you can easily do the same. I've taken our original position versus count data and plotted it on a graph. You can see how this graph and the details of this graph relate to this table. And the question now becomes, what's the trend of these points? We could fit a straight line, something like so, but it wouldn't be a good fit. Okay, it's very clear that you have an upward curvature. So, given that there's an upward curvature, we can speculate. Okay, let's see, we've got an upward curvature. Could the graph be quadratic in nature? In order to answer that question, let's go ahead and sketch a smooth curve through these points. Now these points lie pretty close to a good smooth curve. So I'm going to just draw a smooth curve, something like this, going through some points, not through others. Looks like there are more points above the curve than below, so I probably should have raised it just a little bit. But let's take this as a basis for a quadratic model. Okay, well, our quadratic model is going to be y equals at squared plus bt plus c. Now there's reason to believe that the velocity was 0 right here at the beginning point, right here at t equals 0. So let's assume v equals 0 and t equals 0. Now v is just the slope of this graph because the rate of change of position with respect to clock time is the slope of the graph. So the slope at t equals 0 would be 0, meaning that if this is a quadratic function, this is your vertex. So vertex is the position. Now actually we got the position at t equals 1, so we might extrapolate backwards and assume that vertex occurs at position, say, 28. That would be pretty consistent with this data. Or that 0 count 28 centimeters. So let's assume the vertex is at 0.28. Then the graph, we know that y will equal let's put the equation in the form a times t minus h squared plus k. And this tells us that h is 0, because if the vertex, if the axis of symmetry is on the axis, on the y-axis, then we haven't shifted the graph right or left. Okay, so the vertex is here with h equals 0, which is indicated by no horizontal shift. And that's indicated by the fact that the vertex is on the y-axis. And k equal to 28. Of course, standing for 28 centimeters. That's the vertex is at 0.28. So that achieves what we need here And let me move this board over so we can read everything I just wrote. We don't need that data table anymore. Okay, so h is 0, k is 28. What does that leave us? It leaves us only a to determine. So now we know that y equals a times t squared. Since h is 0, t minus h is just t, that's squared, plus k, which is 28. We got to determine a. Well, to find a, let's just take another point on this curve. Now, I don't want to take another data point. The basic principle is you find a point on the curve, you estimate it as accurately as you can, and you use that point. It gets you away from the idea that the best fit line should go through any point. This best fit curve should actually be just a little higher. So I'm going to say, well, if the best fit curve was a little higher, then the point that appears to go through this last data point will be just a little higher. The last data point, y was 82, x was 28, so let's assume that 2884 is on the graph. Now that might or might not be a good estimate. We'd need a much better graph to make a really good estimate anyway, but let's assume that 2884 is on the graph of the best fit curve. Okay, then y equals 84 and x equals 28. So we can put, and it's not x, it's t, so we can put these y and t coordinates into this formula and solve for a. So y equals a t squared plus 28 becomes 84 equals a times 28 squared plus 28, and there's kind of a coincidence. 28 occurred twice here in the y coordinate at this point and as the x or the t coordinate of the estimated point on the graph. That's an accident, and I wish I had avoided that because it becomes a little bit confusing about where these two different 28s come from, but they come from two different quantities that just happen to have the same numerical value. If we were including units with these quantities, we'd be able to easily distinguish. This is 28 seconds, this is 28 centimeters. So that would be a times 28 seconds squared plus 28 centimeters, which would distinguish these two 28s that we just happen to have. Okay, so in any case, we solve this for a, and we get a equals what? Well, 84 minus 28 is 56. Let's just write it out. 84 minus 28 over 28 squared. And that's really convenient. We have all kinds of coincidences going on here, and they're unrelated. 84 minus 28 is 56. 56 over 28 is 2. So just very weirdly, the arithmetic turned out to be, wait, I'm sorry, it's 56 over 28 squared. 56 over 28 is 2. That's actually going to come out 2 over 28 for reasons you don't need to completely understand. That's 1/14, which is approximately equal to 0.07. Okay, so now we have a model y equals 0.07 t squared plus 28. We can test that model. We can plug these different values of t that we have from our data, and I can move this over a little bit again to show that table a little more. Okay. I can plug in t equals 1, 4, 8, 12, 16, and 28 and see what I get from my y values and see how they compare with the y values on my position graph. And probably going to do that in the next clip.